Good morning. Let us continue the problems we were doing together. So first, give the lowest dot symbol for the following atoms and how many more electrons can each atom accommodate. So first, when you have such type of questions, the first thing to do is to go to the periodic table to know in which group you have these atoms. Okay, so we'll start by selenium. So if we go to our periodic table, so it's here. Okay, so this is the periodic table. Let us look for selenium. So it's here. Okay, Se, it's here. So it is in which group? It is in group 6. Okay, so since it is in group 6, how many electrons it will have on the outer orbit? If I want to represent the structure, the Lewis dot structure of Se, okay, so here, whenever you have group 6a, this means that it has 6 electrons on its outer orbit. To make sure of this, you have 34 electrons, okay? So if I have 34 electrons, how they will be dispersed? If I have 34 electrons, I will have 2 on first orbit. I have 8 on second one. Okay, I have 8 on the third. So until now it's 2 plus 16, it's 18. So I still have 16 to reach 34. Okay, so I have 8 on fourth. So until now, 8 times 3 is 24 plus 2, 26. So I just still have uh, 8. Okay, I still have 8. So look here, you are not responsible of this part. Okay, you have in some cases, when you go beyond the fourth line, you have a certain group B in between. Okay, but you are not responsible of this. I will not ask you to know how to do the distribution of electrons in these atoms. Okay, so you just, because it's little bit, it's more related to chemistry, it's a little bit complicated. So if you want, what you can do, whenever you have an element here that is beyond the line 4, okay, no need to put in order to find the number of electrons on the last orbit, just look at the group. So since it's group 6, okay, you will have if you want, in this case, you will have 6 electrons on the outer orbit, because here as you can see, you have from here to here, okay, you have 9 elements. So in this case, the planetary model is a little bit different, okay, but you are not responsible in drawing the planetary model in this case, okay. So what I want from you, so just you should know to draw the planetary model for these parts above, when you don't have group B, okay? While if you have it in the line after line 4, if you have a group B, just look at the number of electrons on the outer orbit from the group. So since it's group 6A, so it will have 6 electrons on the outer orbit, okay? So you can just say, since it is in group 6A, okay, 6A. Then it has 6 valence electrons. So we say it's 6 valence electrons. So it means that it will have 6 electrons on its outer orbit. Then it will have 6 electrons on its outer orbit. Okay. So if I want to represent the Lewis structure, so if I go back to the structure, okay. So this is SE. I just put 6 dots around SE. So it will be like this. 1, 2, 3, 4, 5, and 6. Okay. So SE can do covalent bonding or can do ionic bonding. It depends on the other atom. So for example, if I combine Se with oxygen, what will be the type of bonding? What will be the type of bonding if I combine Se with oxygen? Yes, very good. It will be covalent. Why it will be covalent? Because Se and oxygen both needs only 2 electrons to close their full set of electrons on the outer orbit. Okay, so if I combine it with oxygen, I will have covalent bonding, since if I put O here with it, okay, then O is having also 6 electrons on its outer orbit. So 1, 2, and 3, 4, 5, and 6. So what O will do, they will share together 2 electrons. Okay, so, and by sharing together 2 electrons, each one will have 8 electrons on its outer orbit. So in this case, Se will do a covalent bonding with oxygen. Now, if I combine Se, for example, with Na, what do I get? It will be covalent or ionic in this case? So try to combine Se with Na. What do you get? Which ionic compound you get? Yes, it's ionic, but what is the molecule you get? How much sodium elements you need to combine with selenium? So you can see here that Na is in group 1. So it has 1A. So it has 1 electron on its outer orbit. Okay?
We need 2 Na and it becomes Na minus, Na plus.
Very good. We need 2 atoms of Na because each atom of Na will lose 1 electron to give Na plus. And since Se needs to gain 2 electrons, so we will need 2 Na plus with Ce minus. Okay. So if we combine with Na, we know that selenium will give us the ion Se2 minus. So it will need to gain 2 electrons. Okay, it will need to gain 2 electrons. Okay, so we should combine it with, so it should be combined with 2 atoms of Na. So it should be combined with 2 atoms of Na, which will give, which compound? It will give Na2 Se. Okay, Na2 Se. So it's an ionic compound. We can write it in this way: 2 Na plus Se2 minus. Okay. Okay. Now the second element they gave us to draw its Lewis structure is krypton, Kr. So as you can see here, where is krypton? So krypton is in group 8a. This means what? How many electrons it's having on its outer orbit? It's 8 electrons. Okay. So what can we say? Since it already has 8 electrons on its outer orbit, then it's in a stable state. This is why we say that the elements in group 8a, okay, these are noble gases. They don't need to interact with any other atoms because they are already stable. Okay, so if you want to illustrate the Lewis presentation of krypton, so this is Kr, and it's having 8 electrons on its outer orbit. So it's stable and don't need to interact with any other atom. But who will tell me? Sometimes in molecule bonding, we have one type that can take place between noble gases. Which type of molecular? No, yes.
Secondary bonding.
Yes, secondary type. But even in secondary type, you have several possibilities. Which one is involved in case of atoms Kr that are bonding together?
London dispersion.
You have dipole-dipole
not sure.
interactions. Yes. If you look back here, look, it's here. When we went through secondary bonding, okay, in secondary bonding you have different types. The first one is you have dipole forces, okay, which arise in molecule comprising two atoms with equal and opposite electrical charges, okay, or you have the second one, which is London forces, which are attractive forces between non-polar molecules. So here we are in the case of London forces. If we have an atom that is having a set of 8 electrons on its outer orbit. Okay, why? Because if it has already, as you can see here in this example, you have these two atoms. Each one has 8 electrons on its outer orbit, so they are already stable. Okay, and they don't have their charges, they are neutral. Okay, so each atom, this is why we say it's an attractive force between non-polar molecules, because each molecule, okay, is in total, as total balance, it's 0, but due to if you want, due to the motion of atoms or molecules, so when the molecules will move, we will have certain dispersion of electrons. So we will have zones with a higher number of electrons than other, which will cause a certain, so here, for example, when electrons will move, this side will be, it's creating like an unbalanced charge. Okay, this side will be more negative. Okay, so since this side becomes more negative, it will attract, for the other molecule, it will attract a side that is less negative. Okay, so relative motion of electrons can create can create dipoles if you want. Okay, so if you look at the molecule as overall, it's a non-polar molecule. Okay, but since due to motion of electrons, you can have another dispersion, a new dispersion of electrons, in a way to create, if you want, for a certain, it's not a permanent, also it's not a permanent force. In general, London forces are weak. Okay, they are weak because this position of electrons is not permanent. So if I look at another instant, I will have a new distribution of electrons, so this attraction will not be permanent. Okay, so this is why they say it's temporary dipoles, where I can have electron on one side that will attract a positive side of the other atom. Okay, so whenever you have an atom of group 8, yani if you have several atoms of group 8, they can attract between each other through London forces, because once they move, they will have a new dispersion of electrons, which will create certain temporary dipoles in these atoms, which will allow them to attract by London forces. Okay, so here we can say that this is an example for krypton. Okay, if I have two krypton atoms, they can connect by London forces. Okay. Now, let us continue. So this is for question 4. Okay. Of course, how many more electrons each can accommodate? For Se, it will be 2, as we said. For krypton, 0. Krypton do not need to have any additional electrons because already it has a stable set of 8. Now, another question. Based on Lewis dot symbols, predict the ion given by the following elements: Be, F, P, and Ts. So of course, the strategy is, in such case, okay, in order to determine the ion resulting from an atom, okay, we should find the number of valence electrons. Okay, the number, when I say valence electrons, this means the number of electrons on the outer orbit. Okay, the number of valence electrons on the outer orbit, which can be known from the group. Okay, which can be known from the group using the periodic table. Okay, using the periodic table. Okay, so now let us start with Be. So if we look at our periodic table here, so for Be is here. It's group 2A. Okay, so it's a metal. Just one information. Okay, in general, so as we said, metals are in general, the majority of metals are group 1, 2. Okay, 1, 2A, and also as I told you, you have groups B. Also, groups B are within metals, but as I told you, are not. You don't have to know the difference between A and B. It's fine. It's more chemical. It's more details in chemistry. Okay, so just you should know that here metals are in this zone, so they involve nearly groups 1A to A, and nearly all groups B. Okay. Also, in general, you have some metals in 3. Also, group 3A the majority of them are metals. What is the idea? You know that a metal in general can give a positive ion. Okay, so whenever you have group 1, 2, 3, so it will tend to lose ions, lose electrons to give ions. Okay, this is why groups 1, 2, and 3 almost are metals. Okay, so here we have that Be is of group 2. Since it is of group 2, so it will tend to lose 2 electrons in order to give the ion Be2+. Why? Because the atomic number here is 4. Okay, so it has 2 electrons on the first orbit and 2 electrons on the second one. So you know that the full set for the second orbit is 8. So it's very far from 8. This is why it tends to lose 2 electrons, okay, resulting in Be 2 plus. If you want to write the analysis, we just say Be is of group 2A. So we can write that Be is from group 2A. So it has 2 electrons on its outer orbit, and the orbit is the second one, okay, on its outer second orbit. Which is very far from the stable set of 8. Okay, so it will tend to lose two electrons, okay, 2 electrons to give the ion Be2 plus. Okay, now sometimes they can ask you to draw the planetary model for an atom. Okay, what they mean by the planetary model, it's the representation of the atom with all its orbits. For example, if I want to do it for Be, this is atom Be, okay, and this will help you to see how many electrons you have on the final orbit. Okay, so since the atomic number of Be is 4, okay, so on the first orbit it will have 2 electrons, because you know that the first orbit can have maximum 2 electrons. The second orbit can have up to 8. Okay, so here this is 1, this is 2, and the outer orbit will only contain 2 electrons. Okay, but as we know, the stable state of the second orbit is 8 electrons. This is why what will happen here is that Be will tend to lose these 2 electrons in order to give you Be2 plus. So if I, after losing the 2 electrons, the planetary representation of the ion is like this. So Be2 plus will only have electrons on the first orbit. So these are the 2 electrons. Okay. Now, if we continue for the other, and it's the same procedure, so we can just do it in a fast way. We have F, B, and CS. If we go to the periodic table, if we have F, so for F, what will happen? What will be the resulting ion for F? So first, it is in group 7. Okay.
Gain of electrons, so F minus.
Yes, it will give us F minus ion, because F is in group 7, so it will have 7 electrons on its outer orbit. Okay, and this will lead to it needs only 1 electron to close its set. So if you want to represent the planetary model for F, the planetary model for F is like this. This is F. This is the first orbit. It will have 2 orbits since the number of electrons is 9. So this is the first orbit. This is the second one. On the first orbit, it will have 2 electrons. On the second orbit, it will have 8. So 7. Before gaining an electron, it has 7. So 1, 2, 3, 4, 5, 6, and 7. This is the planetary model. So this is the planetary model for atom. For atom F. Okay. And then, since it has 7 electrons on its outer orbit, it's very close from the set of 8. So it just needs to gain 1 electron to form the ion F minus. If I want to represent the planetary model for F minus, so I will have 2 electrons on the first orbit and 8 electrons on the second orbit. Okay, so it will be like this: 1, 2, and 1, 2, 3, 4, 5, 6, 7, and 8. Okay. Now, if you have in this case, okay, the ion will have a full set and it will be stable, and it can connect. F minus can connect with another ion of opposing charge. So if you have F minus and Na plus, the opposing charges will attract each other, forming an ionic compound. Okay. So for the other examples, we have B and Cs. So also let us look at the table. For B, so this is B. What will happen for B? What ion B will give me? Yalla, who will tell me?
You have 2 electrons on the first shell and 3 electrons
Okay.
on the second one.
Very good.
So it will lose 3 and become Be 3+.
Yes, very good. So since the atomic number of Be is 5 and it is in group 3a, so it has 2 electrons on the first orbit, 3 electrons on the outer one, and therefore 3 is far from 8, so it will tend to lose 3 electrons to give me B a 3+. Okay, so here I will have the ion B3+. Okay, and finally the last example is Cs. So for Cs is here. As you can see, Cs is in group 1. So it has 1a. It has 1 electron on its outer orbit. So it will tend to lose it to give the ion Cs+. Just one remark. All elements in 1a have in common that they have 1 electron on their outer orbit. But all of them are metals except hydrogen. Okay? Because hydrogen is a specific case since it has only 1 orbit, which is the first orbit. So in general, as you can see, hydrogen here is mentioned in group 7 because it will tend to just gain 1 electron to close its full set. Okay, so IH is not a metal; it's an exception. Okay, because it has 1 orbit and it tends to share an electron with another atom in order to reach a stable set of 2 electrons on its outer orbit. Okay. Any question on this? Okay. So let us continue. Problem 6. Draw the Lewis electron structure for the following molecules. So first, we want to draw the Lewis structure for Br2. Okay. Whenever I want to draw the Lewis structure for a molecule, I should try to to see, first I should determine the number of valence electrons. Okay, so as usual, I go first to the periodic table. So in the periodic table, you can see that Br is in group 7a, as you can see here. This means that it will have 7 electrons on its outer orbit. So if I want to represent Br2, I will put 2 molecules. And since the 2 molecules, the 2 atoms Br, okay, has 7 valence electrons. So what will be the type of bonding between them? What will be the type of bonding between the 2 Br atoms? Yes, exactly. It's a covalent bonding, okay? Because Br, each atom needs 1 electron to close its set of 8. Okay, so they will share together 2 electrons in this way. So if I draw if I represent the Lewis electron presentation, I have this. I will have 2 electrons shared. Okay, so this is Br. So I have here an atom Br and here another atom Br. They will share 2 electrons together. And in this way, they will have a set of 8, okay? Because already Br has 7. So each atom will have this 1, 2. So each atom will have 6 electrons already present, okay? And 2 electrons that are shared. So these are 1, 2, 3, 4, 5, 6. We already have, sorry, it will be 1, not 2. It's 1 bond, not 2, okay? So just here one line, okay? Because it's already, you will have a double bond if you have 6 valence electrons, okay? But if you have 7 valence electrons, you need just 1, if you want to share 1 electron, okay? So this is number 7 for each one, and it will share with the other atom Br electron number 7. So now if you count for each atom, it will be 8. It's 1, 2, 3, 4, 5, 6, 7, 8. Okay? So here, for the second atom, it's similar. If I want to draw them, so I have 1, 2, 3, 4, and 6, 7. And, sorry, 5, 6. Okay? And electron number 7 is shared with the other atom. And in this way, these 2 electrons are common between the 2. Okay? Since they are common between the 2, if I count for Br, the number of electrons, I will take them into account. So here I will have for each atom Br 1, 2, 3, 4, 5, 6, and 7, 8. Okay? In this way, it will be a stable molecule since each atom will have a set of 8 electrons on its outer orbit. So this is for molecule Br2. Now, the other molecule to draw the structure for is CH3Br. Okay? So already we have seen that Br has 7 electrons. So I will try to present, first Br. So since it has 7 electrons, 1, 2, 3, 4, 5, 6. Okay. Now, 7. I have in this molecule atoms Br, H, and C. I should connect Br with C or H. Who will tell me? Yes, exactly, with C. Why not with H? Because if I connect it now with H, okay, I will have a stable molecule. So I will not have a place for C. So if it's wrong to connect Br with H, because if I connect it with H, I will get the molecule HBr, and I will not have a place for C. So I cannot do this here, okay, since I need to include also C. So I should connect to CBr, okay, and C can share 4 electrons. So it will share 1 with Br and the other 3 will be shared with H, okay. So this is C. We know that C have 4 electrons, 4 valence electrons, so it can share 4 electrons. The first one is already shared with Br, so it will still have 3 electrons to share. It will share them with H, okay. So we have here H, H, and H. Okay. In this way, by doing this, if we count the number for each atom, we will see that it satisfies the equilibrium state. Okay. Because for H, each H atom will have on its outer orbit 2 electrons, which is equal to the full set because it just has 1 orbit. So as you can see here, if you count for H, you will count these 2, 1, 2, okay? Because the shared electrons are counted for the 2 atoms, okay? So here I can say that H will have in common with C these 2. So in its outer orbit, H will have 2 electrons. The same for the other H atoms. Now for C, when I count the electrons for C, I will count also the shared one. So I have 4 bonds for C. Okay, so it's 4 times 2, 8. So C has 8 electrons on its outer orbit. So it's in the equilibrium state. And for Br also, it's 1, 2, 3, 4, 5, 6. And I count these 2, it's 8. So also Br here is, it's fine with Br. Okay, so this is the Lewis electron structure of the molecule. Now for O2, okay, whenever I have 2 atoms, from the same atom is doing a interaction with himself, okay, with another atom like him, then it will be a bond, a covalent bonding, okay, because this, of course, if the number of electron of valence is higher than 4, okay, because if you have a metallic compound, then what will happen that the number of electrons is not enough to share. So we will be in the case of metallic bonding. So the electrons will be shared between all atoms, and they will form a cloud of electrons. This is the third possible type of bonding between atoms, which is metallic bond. Okay, but when we talk about atoms with more than 4 electrons, then it's a covalent bonding. I will open a new session to continue. Okay, it's the same link.